Hi. In preparation for today's video, I started putting together the circuit simulation in Circuitverse. And I had an epiphany during that, and I think I'm going to be able to simplify my design. I'm not going to say significantly, but I'm going to be able to simplify it based on this epiphany. And I want to share that with you and get to building some more. Let's go. Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey. Let's start with the circuit simulation that I was putting together. Now, I am leveraging the ALU flags module that you saw last time and that I've built onto the breadboard. These are the two sets of flags that I've actually built into the breadboard at this point. And so I'm leveraging these as subcircuits in this design. Now, I had originally thought I was going to be outputting the state register off of these flags by hard coding a 0 or a 1 value on here, and I realized as I was putting this together I really need to be able to toggle back and forth between these to decide which of the two sets of flags are actually asserting outbound. So when this is 1, the interrupt flags are being asserted. When this is 0, the program flags are being asserted. And keep in mind that this is an active low enable signal. Then I started looking to see what it would take to implement the 74HC151 IC. And it takes 3 inputs plus an enable, so I was going to use these 4 signals to handle half the outputs and then duplicate this for the other half the outputs so that I was able to handle all of the different 16 states that were required in order to determine whether or not a particular instruction is executable or not. And I started thinking about how I was going to be able to do that and the timings required for that. And then so what would end up happening is these 8 different conditions would be handled by one of the 151s, and these 8 conditions would be handled by another 151. And the original intent was to use this most significant bit here to determine which one was enabled. That would require an inversion of one of those bits, or that most significant bit, to make the determination. But then I started thinking and I started to realize that these are actually built out in pairs. And it's not necessarily that I need to have the inverted signal. What I need to be able to do is just invert the condition when it's been selected. So rethinking this, if I was to take these 3 bits to select on the 74HC151 and then this least significant bit, then would determine inversion, whether I invert a signal or not. That could save me quite a bit. And moreover, I don't believe I would be adding any time, because that inversion could be determined and calculated in parallel with the multiplexer, such that it would be ready to go at the point in time when it was needed. So let's take a look at this and see how that would work. So 0 and 1 is a constant 1, and an inversion of that is very simply a 0. That's trivial. Equal and not equal are very simple inversions of the Z flag. Again, that's trivial. The C flag for carry set, carry clear, again, trivial. Minus or negative and then positive or 0, so that is the N flag. Again, trivial. And finally, overflow set and overflow clear. That's a trivial condition as well. Now we get into some that are a little bit less trivial, and I want to walk through these a little bit slower. So unsigned or higher has a binary or multiple condition, not binary condition, but a multiple condition, indicating that my Z flag has to be unset and my carry flag has to be set. And while I have to now extend the inverted Z flag off the flags to do this evaluation, what I don't need to do is calculate this using the inverted carry and the natural Z and then put that through an OR gate, because C equals 0 or Z equals 1, if you want to calculate the inverse of that. Okay, I made a bit of a mess trying to explain this, so let me try again here. So my condition was when C is equal to 1, the carry flag is equal to 1, and the 0 flag is equal to 0. Or when I have C set and Z unset, or C and not Z. Here's the truth table that comes up from that. And so you can see column X ends up being the result of whenever C is set and Z is not set, X is equal to 1. It's a pretty simple truth table. The other condition I was checking for is when C is equal to 0 or Z is equal to 1, which can be distilled down to not C or Z. And again, this is the truth table for that. And as you can see, column Y is set when column C is 0 or column Z is 1. And if you haven't figured it out, I'll call it out specifically. X and Y are actually inverses of each other. And in fact, if I set them side by side, you can tell that column X and the inverse of column Y are exactly the same, and column Y and the inverse of column X are exactly the same. And so in Boolean algebra, if you have A or B, that can also be expressed as the inverse of not A and not B. And A and B can also be expressed as the inverse of not A or not B. And this is the specific piece of logic that I'm planning on taking advantage of. The key here is I don't need to do that final inversion because I'm actually looking for an inverted result. So rather than inverting twice, I just remove the inversion to begin with, and I end up with the result I'm looking for. The next one's a little interesting as well because I actually need the inverted L flag for that to work. And again, my L flag is where L is not equal to V, and that's run through an XOR gate ahead of its presentation off to the control module. But then its inversion is simply the L flag. So that still holds, but I need to extend the inverted L flag off to my control module. And then the last two, greater than or less than or equal, are, again, you've got this multiple condition situation where you can use simple Boolean algebra to change that and just invert the result of this first one. What does that do for me? Well, that ultimately means that I can get down to 174 HC 151 with an exclusive OR gate to handle this least significant bit to determine if I'm presenting the natural state or inverting. And then I just present the results of my 151 as one side of that exclusive OR, a 1 or a 0 to the other side of that exclusive OR. All right, is that going to work? Yes, it will work. Because the 1 or the 0 is going to come from this least significant bit. I lost track of myself there for a second. So yes, the least significant bit is going to determine whether or not it's buffered or inverted. And then the result of all of this evaluation is going to be the other side, which is going to be the output off the 74 HC 151. So yeah, that's going to work just fine. And then I can turn around and present that to determine whether or not we're going to execute the instruction or convert it to a no-op because the condition failed. That was my epiphany today. Okay, so what flag signals does that leave us with? So basically anywhere where the least significant bit in the conditions flag column was 1, I blacked that row out. I highlighted any column where I still had a flag that I needed. And I got what looks like a bumblebee, so I condensed that down a little bit. And so these are the flags that I really need to carry off the board here. I don't need anything more than those 6. I had originally intended 10. So the flags that I need to carry off the ALU into the control circuitry are just those 6. Let me clean up the circuit verse model, and I'll come back when I have that done and show you what the result is. Well, I was able to simplify this from 4 line drivers down to 2. That's now 1 for each set of flags, which is an amazing simplification. I did take out the inverted LEDs, and so I'll have a line driver which drives those as well to make sure that I am not putting any load on these signals. And then of course I've got the 6 flags exiting this particular module, and that's going to make life much easier for me when I get into determining whether or not a condition has been met or not, as I talked about in the previous segment. I did add back in this 0 and 1, so 0 being for the program flags and 1 being for the interrupt flags for the context. These being HC or CMOS related ICs, I have to tie the unused inputs one direction or another. I am not using it, so you can see the output of that particular flag is not going anywhere, but I figured I may as well go ahead and tie them independently so that I can make use of them pretty easily in the future without having to change the design, if I so decide I need to pull that off the board. Let's put this together. Okay, here's the flags as we left them last time. And now it's time to add the 74 HCT, actually is what I've got, 541 ICs. I need 2 of them to take the signals off the flags and then merge them together so that they go out onto the, back to the control module. And then I need another one to drive the LEDs. Okay, this line driver is always going to be outputting, so I can take pin 1 low and I can take pin 19 low. That way it's always got output going. The other 2 have, I can take pin 19 low, and that will leave pin 1 available for, so I want to do 19 now. I think it's probably going to be easier because the exclusive words that are going to drive that are up here. So let me take pin 1 low. On one side I need pull down. On the other side I need, well, not pull down, but I need a low signal. On the other side I need a high signal. So my control signal is going to be here, and that's going to go to my joined exclusive ORs. The output here, which is going to be the buffered version, is going to go to the program. My inverted is going to come all the way over here to this, which is going to be my interrupt. I'm looking at this and I'm thinking I've got this in the wrong spot. Yep, that looks better. That's the way it was lined up before. So now I need a signal wire to bring this either low or high, depending on what's going to be asserting. There it is. So from left to right here, I've got Z, C, N, V, inverted L, and then I've got the inverted Z, and then I've got L all the way to the end here, which would be used just to light up the LEDs. What a mess. Let me get this cleaned up. but it looks like I've got everything wired up. I can take from this point, or this point in order to get my outputs out onto back to the control logic. And from here I can go into my LEDs. Speaking of which, I had soldered one of these up in a prior video, and what I really need is not quite so big, so I'm going to do another one here. I need 5 LEDs. I've got this 8-way LED graph here, and I've got these cheap thin turn pins that bend and twist and do whatever. I'm going to use these on this board. I've got to find some use for these things. And I've got the microscope out, so let's see if we can get going on this. Much smarter about it this time. All right, positive, ground, plug that in. Yep, all good. Okay, last thing here is to hook up the LEDs. Now I've got a mark here that shows positive on this side and negative on the other side. Let me switch my glasses so I can see that a little bit better. And so it should be literally as easy as dropping it in here, and then I've got to hook up ground on the opposite side for everyone that I'm going to use here. So let's see if I can find some of these longer ground ties. And then it really should be literally a matter of hooking the outputs up to each flag. So 0, carry, I believe it's negative, overflow, and then the L flag. I'm gonna get that wired up. Let's turn this on. I did hook up all of these wires here and brought them all up to a high state. I did some testing, it didn't work out well, and unfortunately I had the board down here like this, and so I didn't actually record it. But what I did discover is I had this down to a low state, this being the clear signal, and so no matter what I did, it was always clearing. And so when I changed that back to being at a high state or plugged into 5 volts, things started working better. So if this is set carry, I take that low and the carry indicator comes on, and then I set it back, and I'm gonna grab a pointing device here. So this one's unused, 0, carry, negative, overflow, and less than. And then these two are not used either. So I can clear carry, or I can set carry. And then I also have the ability to switch to the, let me make sure I'm doing this right, because high should be the interrupt and low should be the program, and I've got that backwards. So that would be easiest done by switching these. Let's try that now. Got that plugged into the wrong spot. Alright, so clear carry, set carry, clear everything, set carry, and switch to the interrupts, which is going to be blank. This one is latch the 0 flag. Let's make 0 flag low. Latch the 0 flag. This one is, let's make the carry flag low. Latch that. Bring the carry flag back high. Latch that. That's good. This one's the negative flag, and that's the latch. And then at the same time, I can latch the less than. If I take that low, that latches, and if I latch less than again, that works. This one is the overflow flag, and again, less than works, and less than works. I still have the carry flag set, so let's clear the carry. And that all works just fine. Now, the other part of this is I've got signals to bring up here to the interrupt side, and those are going to be each of the latches, and the clear and set carry, and then each of alternating across here, each one of those latches need to come up here as well. But I'm not going to do that right now, because honestly, it's just going to end up being a mess until I can get everything pulled together. So I do have my signals documented. This goes from right to left. So clear carry, set carry. The Z data needs to span both, but the Z latch needs to have separate signals, one for the program and one for the interrupt. Carry data, carry latch. Negative flag data, negative flag latch. Overflow data, overflow latch. And then the less than latch. So I need to hang on to that because that's my crib sheet for my flags register. Okay, that's going to take care of the 2 flags registers. I'm going to call them registers simply because they're storing data, but I have no way of directly manipulating that register other than the clear carry, set carry instructions that I'm planning. I'm not planning on having them be able to be pushed to the stack or loaded into any other register at this point. I may reconsider that at some point in the future, but there's no plans for that. There are 2 registers, one for the programs, one for interrupts, which means that I've got a context that I'm going to have to manage. And that should be relatively easy to do, but that will be done in a future video. Now, the next video related to the ALU, I need to take these flags and integrate them into conditional execution. My plan for the moment is to be able to indicate when that condition would be set or not set. I also need to take and expand from an 8-bit instruction to a 12-bit instruction and clean up the issues that results in related to the main bus assert. So there's going to be some pretty hefty changes related to this that come up in the next few videos. The very next video, on the other hand, is going to be soldering up the backplane for my registers. I have just about every component I need with the exception of the USB related stuff at the top. Those are expected to arrive in 3 days? No, 2 days. 2 days from today as I'm recording this. So hopefully I will have them. If I don't have them in time for the video and the final production of the video, then I will have them shortly after, and it'll be a quick add to turn around and add those into the circuitry. So look for that. And I'm excited to get into the backplane solder up so that we can start making this 16-bit computer from scratch actually look like something more than just breadboards. Thank you. We'll see you soon.